So when it says electron rich, what does that mean about the bond? A lot of electrons, right? So we have 3 varieties of that. So we have electron rich with 2 electrons, which would be a what? 2 electrons, single bond, 4 electrons, double bond, 6 electrons. Okay, so the more electron rich the bond is, the what? The greater the bond energy. Okay, so that's the bond dissociation energy, BDE, bond dissociation energy. So it's just showing you how much energy it would require to break that bond. And so I said, remember, it's always positive, which I'm telling you it's always what? If the bond dissociation energy is positive, it's an endothermic process. So remember that that's the karate chop, right? So you think about that as you consider the bond energy. And if the bond energy is greater, the what happens with the length? Gets shorter, because as the nuclei attract the electrons that are in the internuclear area, internuclear axis, the bond just shortens up because it's got a super high attraction. All right, so you're drawing these. This might take you a minute, okay? I want you to consider, these are like structural, so they kind of tell you what's attached to you. So consider how you can draw all those Low-Stott structures. And those are positives and negatives on the end.
Teachers, this is just a reminder of the PDs that will be held today. 10 minutes into each class period, or each period. The first session will be held in Ms. Helms' classroom 2306. Thank you.
So these are structural, again, they are listed kind of in the order in which things are bonded. So like you got N with 2 H's, and then you need to figure out where your O and H go, but make octet happen. This goes N, N, O. This says N, 2 O's. N, N, O, it's not N, O, N. And the rest of them I think you guys can see. Let's check where we are. On the first one, give me a thumbs up with your N with the O and H on the end. Okay, so we can have N with two H's like this. What do we usually call that? Amine, right? So that's just like our, like, think of ammonia, and it's similar to that, so it's an amine. And then keep going. It's N triple bonded to N and O, and then we have a cation over here. So on your cation, when you're counting up, you have 5 valence electrons from nitrogen, 6 from oxygen. What happens when you have the plus charge? Subtract 1 from the overall. So it's 10 valence electrons. We have a triple bond. And then the last two have resonance structures, so I did draw them so that we could think back to how that affects bond length when we consider that overall superposition of the bonds. We have a single and a double and a single and a double, but really we don't have either. What is this length? Is what? 1.5, right? Because this extra bond that we are showing as a double bond is superimposed across the entire molecule. So it's neither here nor here, it's spread across the entire thing. So we're going to call that not a single or a double, but a intermediate, which is what? 1.5 bond. Okay, so it is talking about the N to O bond. We're going to order these in length, or order these in decreasing length. Oh, shortest to longest. Okay, so this one's a single, right? So I'm going to call that just a 1. This one is a, no, it's the N to O, right? The N to O. So another single, right? So those are tied right now. But when we look at this, we see this one is surrounded by just kind of all single bonds and really small atoms. Hydrogens are pretty small. But then we see this one is surrounded by a triple bonded N. So what this can do actually, and we could just call them equal, but we can think deeper, this can cause contraction. And so if it contracts a little bit because of this electron density over here, this might be just a little shorter. Just barely, but it's just going to be a little shorter because of this contraction. Obviously we have a triple bond, so I'm going to call that a 3. And then we have down here 1, 2, 3 resonance structures, all of which have 4 bonds total, but across 3 structures. And we kind of divvy that up. What do we call that? That bond length or bond strength. A 1.33. So essentially, this extra bond is equally spread across 3 areas. So 1 divided by 3 is 0.33, which is why we're calling each of these a little stronger than a 1, but not quite a 1.5, not a 2. So the way we did that earlier this unit, we said 4 bonds, 1, 2, 3, 4. We divided by 3, and that's how we got 1.33. All right, so now order these. Let's call them out as 1, 2, 3, 4, 5. Okay, so who's the longest? Which structure? Which structure? Sorry, let's call these out as 1, 2, 3, 4, 5, so we don't have to say the formulas out. So who's longest? Who's the longest? 3 is a triple bond, right? So it's the what? It's the shortest, right? Okay, so who's the longest? 1, okay? Okay, so 1 is the longest. Oh, sorry, we're going shortest to longest, my bad. Okay, now, sorry, you're saying 3. Who's the shortest? 3, okay. And then, because it's a triple. And then who's next longest? 4, because it was the 1.5, so it's not quite a double bond, but it's a little bit longer. I mean, yeah, a little bit longer. So that's number 4. Okay, who's next? 5 is the 1.33 bond. Next. Which one? 1 is a little bit Oh no, sorry, 2 is a little bit shorter than 1 because of that contraction we see happening with the just the environment that this bond is in. So this is the shortest, blah blah blah. Number 2 is the almost the longest one, and then this single bond here will be our longest of them all. Got it? Yeah. For this one, well, 1, the formal charges work out. And 2, and a lot of times, if I just told you guys from the front, this was in the structural format. If you put the O in the middle, you would have had the negative formal charge on nitrogen, which it's not the most electronegative element, so we tend not to put negatives on the most, unless you're the most electronegative element, you don't get a negative formal charge. Okay.
It's kind of like charging with the NO2.
This one?
Yeah, so also it wasn't written structurally.
So this one, I was ordering, it showed us this, well, this one we chose the central atom 1, because we've drawn this one before,
Yeah.
and the nitrate before, so these are 2 very similar polyatomic ions that we've considered before. Nitrogen chooses to be the central, not really, well, actually it does work out its formal charge, so 1, 2, 3, 4, 5, formal charge of 0, formal charge of 0, and then this one has a formal charge of what? Everybody. 1, 2, 3, 4, 5, 6. So formal charge of 0, right? Because oxygen should have 6 valence electrons. It does have it assigned to it, so it's a 0. This has 1, 2, 3, 4, 5. Nitrogen has 5 valence electrons. It has 5 assigned, so it's a formal charge of 0. So these are 2 currently stable atoms, and then we have whatever here. 7, so that gives us a formal charge of -1. Oxygen is the most electronegative. It gets the -1, and that satisfies our -1 overall charge that this thing is to have. So I sped up this process. We could have walked through these 3 times to figure out whose formal charge was best. Yeah.
Same thing for the first one. Do you just know, or do you have to do the formal charges? When I did that, I did put nitrogen in the middle. I put the 4 coming off of it.
You put all 4 coming off.
Yeah.
So. Okay, when you start to see some structures enough, you start to know what functional groups come together. Like this is an NH2 group, and this is kind of like a hydroxide or a hydroxyl group, which is an alcohol group. But if you put the 4 on there, your formal charges would have been wacky. So then you would have had to redraw. I just was trying to speed up the process so we could talk about bond length.
Should we do formal charges every time?
Formal charges like are going to determine if your structure is right or wrong. So yes. Okay. All right, so let's go past this. This is all about bond energy, okay? And then we're going to talk about how this, we're not doing this, we already did this. Just a quick reminder, anytime we form a bond, when things come together, why do things come together? Why do things bond? There's a reason. Okay, because of attractions. Reduces the energy of 2 individual atoms. Remember this little graph here? Yes? Okay, so when they're too far apart, they're too unstable. Too close together, they're too unstable. When they're just the right bond length or bond distance apart, that is what we call bond length, but it's going to be a perfect amount of energy, lowest potential energy system we can create. So that energy given off when they bond is the bond energy. And we've read this graph. You guys have this on the first page of your notes from this unit, or this half unit. We talked about this being energy, potential energy. So the dip in the graph represented the bond energy, and the distance on the x-axis from 0 over is the bond length. Length and energy. Remember we drew like oxygen with the double bond and nitrogen with the triple bond. So what was different about the triple bond within this graph? It what? Had a shorter length, so it was closer to the axis, and what? So it had a lot more potential energy in the bond, so it was a much more stable system. So how did that look on the graph? It had a really big dip, right? So it was like way down here compared to like a single bond. So that's just a reminder of what we had already talked about there. And then when we look at a system of bond formation, so this is methane. Actually, this one we're breaking apart. So we have methane, which looks like what? What shape is it? Tetra, right? So it looks like this. And if we break it apart into the individual atoms it's consisting of, we're basically breaking apart 4 CH bonds. So if this is the total amount of energy utilized or consumed, absorbed for this process, how would I figure out the bond energy of a singular CH? Say again? Just divide by 4, right? Can you guys do it in your head? 452 divided by 2 is 26. 26 divided by 2 is 13. 413 kilojoules. Okay. Why is it positive? Because you're breaking bonds. You broke all 4 of these bonds and that required energy, so it's an endothermic process. Okay, so applying this to this question, what is the bond energy for the CCl bond given this information? Go. You don't have to do it in your head, but you know, it's a nice mental exercise to try. Carbon left is 40, right? Carbon left is because it has 4 bands, like one Alright, I feel like that should have been enough time to think about this, but you guys were off in some rabbit hole. We gotta get out of this rabbit hole. Christian, can you tell me how your group is approaching this?
So you do 3 times the 413 that you have over the negative.
Why and why?
Because it's the same bonds, it's going to be the same energy.
Okay, so it's the same CH bond 1, 2, 3 times. So it's the same magnitude, right? But why is it negative?
It's negative because you're creating bonds.
Right, so remember formation of any bond releases energy, and that is going to be a negative value. So each of these 1, 2, 3 will be negative 413 times 3. What is that?
1239.
Okay, so that's the amount of energy given off when CH, CH, and CH forms. So how are we going to find CCl?
You add 1239 to negative 1238.
So negative 1578 minus negative 1239, which is going to add, would give us what?
Negative 339.
Negative 339 kilojoules per mole for a C to Cl bond. Is that greater or lesser in energy than those CH bonds? Why is this one lesser in energy between the C and Cl versus CH? Just decide within your group first. Maybe think a little bit more than just like the next week. All right, anybody's feeling confident here? Raise your hand. Help me out here. Chase the table.
Maybe atomic radius,
What would that have to do with this?
because the steel is larger, so it's easier to take it.
Okay, you got off in a rabbit hole. I liked your first statement, atomic radius. We were talking about bond energy here. So it's not really about like taking electrons from it because they're sharing electrons. We're talking about breaking that bond. So I like what we're doing with atomic radius. Okay. And then C and H right there, approximately the same size. Hydrogen's pretty small. Much, 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 much smaller than chlorine, of course. So, okay. Why would it require more energy to break the CH bond than the CCl bond? Gabby.
Because the electrons in the CH bond are closer to the nucleus, so they're harder to take.
Right. These guys get closer together. You're going to have a harder time breaking that bond. These guys are farther apart. You're easier time breaking that bond. And that all kind of relates back to Coulombic attraction, Q times Q over distance. So this relates to the distance as well. Okay, yeah, so atomic radius comes into play here, so that the closer they are together, the stronger their bond, the higher the energy. So the closer they are together, the what? Okay, the higher the energy. I was going to say stronger the bond, higher energy. Okay, can I go past this? Yes? Pull out your packet, because I think this is, I got 2 more slides, but pull out your packet. I'm going to show you guys where we're going to practice together. Okay. All right, so we remember this formula, this equation, yes? With bond association energy, you have to do what minus what? So broken bonds minus formed bonds, which Cassie said what? Reactants minus products. That is the only time we do reactants minus products in this time. Every single equation like this is what minus what? Products minus reactants, right? So in terms of like relating this back to the endothermicity or exothermicity, I said just pull out your packet. You guys are rifling. I'll tell you where you're going in just a second, okay? You may have already found it, but hold on. Stop rifling. Okay, so in terms of this blank right here, this is energy what to break the reactant bonds put in. So what are you trying to say? This is a what kind of process? Endo process. So this is energy absorbed. Don't forget that's another word we can use, or required. Absorbed is what I was going to work for here, okay? And then this is energy released whenever you form product bonds. So just remember the endothermicity and exothermicity of both those processes. Yeah, we're not going to do that one. Moving on. Okay, so you found this in your packet now. So you have a big, big chart of bond association energies. You'll find a lot of information there. Some of which will be useful for this exercise. There's a little FRQ underneath that. It says table 2.6. It's towards the back. Yeah? Okay. So the top table, notice that everything is written as positive. That's just a reminder again, bond association energies are all positive, positive, positive. Who has the largest-ish bond association energy? What bond? Or what types of bonds? Well, hydrogen and fluorine, why is that one so high? Okay, so they're very attractive. Well, the electronegativity differences makes them very attractive, and atomic radius. Fluorine's like super tiny, so that means they're really close. And you'll notice all the ones with hydrogen are pretty high, because hydrogen's also small, so they get closer. I was looking for my double bond and triple bond, but it's not actually on this one. So triple bonds and double bonds will have higher, of course, because they're stronger bonds. Okay, so these are delta HFs, okay? standard enthalpies of formation. So delta HS, those are for the given compounds there. Of course, that's not a singular bond, so that's why this is not called EDE. Go ahead and try out questions 1 through 5. In other classes, there's coffee all over the floor. You hold on that thing. I know, throw back to equation writing, unit 2.
Oh my god.
I don't think the O bond, the O double bond is on that one. I may have to read that. Unless I just didn't copy my whole paper. You can send a little, yeah, I didn't copy the whole What's the speed of on
Oh, wait, I think.
when you double one
Yeah, I got it now. I was kind Oh, wait, no. Yeah.
They got 1 more minute to finish up through 5. 1 more minute. Don't judge numbers. They don't judge you. Just go ahead and calculate. Alright, and come back to me. Who's done with the delta combustion using bond dissociation energies? That means like number 4. Alright, who's on number 5? Alright, well, I'm gonna roll because I think you guys know what you're doing. Just gotta calculate if I can get this unfrozen. We're not gonna unfreeze the board. Okay, whew. Okay, so you have all the data. You have the bond associations and you have the delta H formations for part 5. So, looking here, we have a thermochemical equation and we are allowed to use what here? Fractions. That's all a lot of you guys are going, oh, I gotta go up. So I heard you say 2, 7, 4, 6. That's appropriate, it's fine, but you just worked harder because you were making numbers bigger than they needed to be. So you can use for thermochemical equations, you can have fractions, okay? So my calculations will be based off this, but yours will be doubled if yours is doubled, of course. Okay, so structural, you had ethane, double bond O, double bonds on your carbon dioxide, and single bonds on your water. Check, check, check. Okay, so whenever you're doing bond dissociation energy and you find the delta H combustion, which is for this delta H reaction, we were just talking about it in the way it's formed with this via combustion. So we're doing reactants minus products, right? So they told you to calculate the energy of the reactant bonds first, and then the energy of the product bonds second. So you have 1 cc for this equation, of course, if yours is doubled, 6 CHs and 7 halves, so 3.5 O double bond O bonds. So all of this adds up to 4,567. Whose is doubled? Who has a doubled number? Who had double coefficients? Just looking to see where we are. Okay, so of course yours is going to be close to 9,000. And then formation of products, 4 C double bond O, or C double bond O bonds, and then 6 OH bonds, because there were 3 times 2, and that gave you about 5,700 kilojoules per mole. Okay, so that's mole of the reactants versus mole of the products. We okay? So all you were doing was adding up. That's all you were doing. So I'll leave that there if you're modifying yours at all. You don't have to modify to be fractional, but this is just a little bit simpler. And now, what do you do to get the delta H of combustion using bond dissociation energy? What do you do?
You need to create the final formula based off of the ones we do inside the increased formation.
No. We're looking for bond dissociation. We're finding heat of combustion using bond dissociation energy, because this is not the answer, and this is not the answer.
4?
Yeah, I'm on number 3, or yeah, 4.
On number 4, you would do the delta H equation with the broken minus form.
Okay, so reactants minus products, right? Broken minus form. So 4, 5, 6, 7 minus 5,706. What is this? Negative. So 227, half that is 1139. Okay, so it's exothermic. Delta H of combustion is exothermic, and it means with respect to the combustion of 1 ethane, it will release overall through combustion 1139 kilojoules. So for 1 mole of ethane, it'll release this amount of energy. If you have 2 moles, it's 2278, right? So you had just doubled energy. But that would not be established as kilojoules per mole. That would be established as just kilojoules. So that's what all this work right here is in green. So this is the best answer, because it's establishing it per mole of 1 mole of ethane being combusted. Again, if yours was double, it'll be higher than that. And then now what do you do for number 5, where it said to utilize the enthalpy values? Hess's law, which is what, JT? So Hess's law would require you, there are 2 forms of Hess's law. When they just say Hess's law, you have to think about what data is provided to you, because we don't have that kind of data. We don't have equations stacked on each other to cancel things out left and right. We just have H of formations. We're doing products minus reactants, that's it. So we have to just write down the equation so we can know whose products and whose reactants. It's a flip from the previous version. So my 2 products were carbon dioxide and water, 2 carbon dioxides, 3 waters with their established values in that little bitty table. Subtract 1 ethane and 7 halves of water. Well, for that, what's the free element delta H of formation? 0, so that's going to be 0 down here. So all your summation of products minus the summation of the reactants, which won't be more than just that, will give you about a negative 1,400 kilojoules per mole. So why are these different? Why was the bond dissociation energy value different than the H of formation value? Any thoughts? They're close, right? I mean, we're not quite the same, but it's close enough to say, okay, we didn't make a mistake. You guys, let me stand on the top of your table. Does it say anything? top of that table. Oh, it doesn't say one here. So, oh yeah, it does. Table 9.9 says what? What's the super one? Those are all averages. And so what they do is they look at a double bond O in a singular just O2 molecule. They look at it in a big organic molecule. They look at it in a simple inorganic molecule. And so what they do is they say, okay, the environment can impact the bond energy, which is what that very first, what was it, N and O, where I was like, oh, you know, the bond energy of N to O is a single bond, but this environment can impact it, make it shorter. The environment can impact a bond energy, so they average them. So which do you guys think is more accurate? First one or second one? Second one, the heat of formation value is much more accurate because this is like the energy of formation of that specific compound. Water, carbon dioxide, ethane, it's not an average bond dissociation energy, which a CC bond could be in anything, right? Not just in ethane. So the averages are less accurate than the heat of formation values. We good? Yeah.
Are you allowed to calculate is there entropy of combustion with entropy of formation?
Yeah, that is exactly what we just did. Yes. Yeah. So basically, you can find heat of reaction, which for this we're calling it out with the true reaction of combustion, but you can find H of reaction by doing summation of heat of formation of products minus summation of heats of formation of reactants, and that's why we were able to do. That's exactly what we just did here on number 5. We use these values. Yeah.
So on the exam, if we were to use whole number coefficients, would we like get it wrong, or do we just have to make sure we write it for one?
At the end, I would ensure it's written as, because if it says heat of combustion or heat of reaction, it's speaking to one of those items that was combusted, so we just adjust it to be per mole, per 1 mole. Okay. I don't know that you get it wrong, so it depends on where the points fall. Okay. All right. So I think I'm done here. Yeah. I was just going to show you guys those. That's not important. Okay. We have multiple choice now, and on the multiple choice, I'm going to give you a Scantron. For now, just write on your sheet. And I'm thinking we have 38 minutes left. But with that time, I'm going to move through question 40. It's wishful thinking. But if you get halfway through, and I said for homework finish about 75%, that puts you around 55, 60. That would be great. Because tomorrow in class I can give you guys. You just got to let me know where you are, okay? So if you need to spread out, spread out. If you want to stick around some, you can. You should be fully capable of doing all of these. Draw the dang Lewis structure.